Okay, so we're going to continue off what we looked at on Tuesday. So remember that the questions for this chapter are due on Sunday, as well as the discussion. So it's on the whole chapter. So any of the material covered in the PowerPoints, the book for chapter 2, or anything on these videos. So we ended last time talking about electron configuration, and we used the periodic table to come up with the electron configuration of neutral elements, where the protons are equal to the electrons. So we're going to take this now a step further and bring in an orbital energy diagram. So what an orbital energy diagram is, it's a way to represent an electron configuration as a picture. Okay, so quick review on the electron configurations. So here I have my periodic table. We learned about principal quantum numbers denoted by this variable n. And what the principal quantum numbers are the numbers on the side of the periodic table for each period, 1 through 7. We use these principal quantum numbers to tell us what row, what period, what level the electrons are in. Then we have the angular momentum quantum number. Well, if we have just the principal, notice, especially when you get in these lower periods, there's a lot of possible elements to choose from. So the angular momentum quantum number is breaking that down for us further and separating those periods into sublevels. Okay, so we denote these sublevels S, P, and D. So D being the transition metals in the middle. And when we talked about these S, P, and D sublevels last time, we said that the S, alkali and alkaline earth metals, these two columns here, have just one orbital. And each orbital can hold a max of 2 electrons. So that means the S level has a max of 2. We can figure that out just by counting. 1, 2. Now I want to keep in mind, I don't think I mentioned this last time, helium belongs in the S block in this case. So he's right here next to hydrogen. So this would be 1 electron, 2 electrons for the principal energy quantum level 1. Okay? So the reason I'm bringing this up, the max of the 2 electrons, the fact that S has just 1 orbital, is because when we draw it in the orbital energy diagram, notice wherever I have S, so I have 1s, 2s, 3s, 4s, these numbers being the principal energy quantum numbers, and then the letters being those sublevels, S. We said S can have just 1 orbital, so notice everyone just has 1 space. Each of those spaces will hold 2 electrons, a max of 2. For the P, we said P, so this section here, the other main group elements, can hold a max of 6 electrons. So since each orbital can only hold 2, that means it has 3 orbitals. So you'll notice when I write the P in the pictorial diagram, there is 3 spaces for those 3 orbitals. Each of these can hold 2 electrons. Okay. And then D, which I don't have pictured here, but I can sure draw one, has 5 orbitals. So let's look at the 3D. 1, 2, 3, 4, 5. So if we were to write the D, it would have 5 orbitals. 2 electrons can fit in each of those. Okay, now notice we went from 4s to 3d. That's something we talked about last time as well. When we get to level 4, principal quantum number 4, we hit the d's for the first time. So it's still 4s because we're in period 4, but the d's, remember, are 1 less than the period they're in. Okay, so that's going to be 3d. If we're in period 5, the d's are going to be 4d, 1 less, so on and so forth. So let's look now how we're going to fill this up. So this diagram here is a representation of an atom. So we have the nucleus in the center, and then these are the levels or the rings surrounding the atom. Okay? So how do we fill this up? Well, there are 3 rules for when we fill it up. First rule being the Pauli exclusion principle. And what this says is there's no more than 2 electrons per orbital. What we just said, no more than 2. But also, they must have opposite spins. So when we're putting electrons in these spaces, we're going to represent those electrons with arrows. When we do that, we want to make sure for every orbital, every space, we have one arrow going up and the other going down. We don't want both of them up and both of them down. They need to have opposite spins, okay? Now, number 2 here is saying off-bool principle. The electrons start filling at the lowest energy level up. We've done this before when we did electron energy diagrams. All that means is when I start putting electrons in here, I'm going to start at the lowest energy level, the 1s, and then work my way up. Okay, I'm not going to skip any. Last rule, Hund's rule, and this applies to P and D sublevels only. So we only want to pair the electrons when we have to. Okay, what that means is if we only have 3 electrons for the 2p, say we only need 3. Well, I want to make sure that I'm going to spread those out and put 1 electron in each of those orbitals before I pair them up. Electrons are negatively charged. They repel each other, right? Opposites attract, but like repel. And since electrons are alike, they're negatively charged, they're going to repel. So we want to space them as far apart as we can before we pair them up. So let's put this to work. Let's do an example. So I'm going to go ahead and do phosphorus. So when I do phosphorus, I'm going to start by writing my electron configuration, and then we will fill in the map accordingly. Okay, so you can kind of see how they work together. So I'm doing neutral phosphorus. So since it's neutral, no charge here, that means the electrons are going to equal the protons. So phosphorus is number 15, so I know I'm going to have 15 electrons. Since it's neutral, I start at the 1s, right here, period 1. S block is the only one in period 1, so it's 1s2. There's nothing else in that period 1. So then I'm done with that row, I go to the next row, just like reading a book, left to right. Once you're done with the first line, you go to the second line. So I'm in period 2 now. I always hit the S block first. Max of 2 in the S block, so 2s2 puts me at beryllium. Then I'm still in period 2, but I hit the P block next. And I want to go all the way through the P block because I'm trying to get to phosphorus, and it's not in the 2 Ps, it's down in the 3 Ps. So the max in the P is 6, so 2p6. So this puts me at neon. Okay, next, I'm done with the period 2, so I go to period 3. I hit the S block first. 3s2. So that's going to put me at magnesium. Then I'm still in period 3. I hit the P block. And now, this 3p, that's where phosphorus is. Which one is it? 1, 2, 3. It's the third one in. Okay, so 3p3, this describes the electron configuration of neutral phosphorus. So how am I going to draw this in an orbital energy diagram? Well, to draw it, I'm going to follow these rules. I'm going to start at the lowest energy level, and I'm going to put all 15 of these electrons, because if you count these guys up here, it'll equal 15, in this diagram. So 1s, it can fit a max of 2. I'm going to follow the Pauli exclusion principle and make sure that I put 1 arrow up and 1 arrow down. Same thing when I get to the 2s. When I get to the 2p, notice it's full. I need 6 electrons in it. So I'm going to fill each of these up with 2 electrons, making sure the arrows are going opposite directions. For the 3s, is that one full? Yes, I need 2 electrons in that one. The 3p, now notice the 3p, there's only 3 electrons, it's not full. So this is where Hund's rule is going to come into play. It says, make sure you put 1 in each. So if I did this, that is incorrect. Okay, because what I did was I paired 2 electrons, and then I have an empty orbital over here with no electrons in it. Okay, electrons don't want to be close. They don't want to be paired unless they have to be paired. So I need to change this. 1, 2, 3, and put 1 in each. And it doesn't matter if the arrow's up or if the arrows are down, just as long as there's 1 in each. The only time it matters whether they're up or down is if you're pairing them. Then you just need to make sure they're opposite. So this is how we would take an electron configuration and apply it to an orbital energy diagram. Now, for practice, what we're going to do is we're going to take this phosphorus electron configuration and we're going to write the noble gas shorthand way. So I can't remember if I showed you that last class or not, so we'll do it now just to make sure you have that information. So for the noble gas shorthand way, how we do that is we look at the noble gas in the row above the element that we're writing the electron configuration for. So what do I mean by that? Well, phosphorus, it's in period 3. So to write the noble gas shorthand configuration, I'm going to look at the noble gas in period 2. Remember, noble gases is this last row here. So these are my noble gases. So what is the noble gas in period 2? It's going to be neon. Okay, so I'm going to write Ne. So this is another way to write the electron configuration of neutral phosphorus. It's just a shorter way. Why do I want to use this way? Well, because if I put neon in brackets, what I'm telling you is start at neon. So you don't have to start all the way at the 1s by hydrogen. You can start at neon instead. So that takes out this whole section of your electron configuration. Okay? So we don't need to write 1s2, 2s2, 2p6, because 2p6, that represents neon. And we just said start at neon, so we don't need to include this part. We just need to include what comes after neon. And what comes after neon is period 3, the S block. So we're still including this last portion. So 3s2, 3p3. So this is another way to write that same electron configuration. All right. So let's do one more. We'll do bromine. You can see this at work here. All right, so with bromine, let's write its electron configuration. You can go ahead and start on that while I get this ready. We're actually going to write this one like you would see it on the homework. All right, so on the homework, it's not going to be leveled like this in a big diagram. It's going to be all flat and straight, but it's going to go in order of energy, okay, starting from lowest up to highest. So to fill this in, you're going to take your electron configuration. Hopefully you have figured that out. Well, it's 4p bromine for the 5th one. So this is my electron configuration for bromine, and I'm going to transfer it and write it down here. Okay? So you would want to make sure when you're filling this out on your homework that for all of the full orbitals, you're putting the electrons one up and one down in each orbital, opposite spins, following that Pauli exclusion principle. When we get to the Ds, remember 3D. So a lot of people put 4D there and get that incorrect. The Ds are always one less than the period they're in. In this case, we're going all the way through the D block. So there's a total of 10. Let's do that the same way. And then when we get to the P, we said we wanted just 5, right? It's the 5th one in. It's a halogen. 1, 2, 3, 4, 5. So that's good. If you count these numbers, you should get the atomic number for bromine because it's neutral, and the protons will equal the electrons. So that should equal 35. All right, so with this, let's do the shorthand way, because that's a long electron configuration. We can cut that down quite a bit. So let's look at how we're going to do that. So to cut it down, we're looking at the noble gas in the row above the element we're describing. So we're describing bromine. Bromine's way down here in period 4. We want to look at the noble gas in period 3 then, which would be argon. So we would write argon in brackets. This is a shorthand. And that would take care of, oops, this whole section here. Right up to 3p6, because 3p6, that's where argon is. So now we include what's left, starting in period 4, 4s2, 3d10. All right, now we're going to look at valence electrons. Let me draw my atom. Nucleus being the center, that positively charged center with the protons and the neutrons in it. And then our shells representing our principal quantum number, so n equals 1, n equals 2, n equals 3, and then this last one would be n equals 4. So in this case, I have 4 shells. So I'm looking in row 4 there. So what is a valence electron? It's the outer shell electrons. It's the ones that we're going to use in bonding. And we're going to see a lot of this in the next chapter, in chapter 3. So I'm talking about just this outer shell here. Okay, so only these blue electrons. The inner shell electrons, the core electrons, are the electrons present on all the other shells. Okay, so why are the valence, the outer shell electrons, involved in bonding? Well, because they're most accessible, number one, but also they're furthest away from the nucleus. And the reason we said that those electrons orbit the nucleus is because the nucleus has a positive center. The electrons have a negative charge, so they're attracted to that nucleus, which kind of holds the atom together. So since these electrons are further away, they feel that pull less. So they're not held as tightly, and it's easier for these to be involved in bonding, whether it's a transfer of electrons or covalent bonding, which we'll talk about in chapter 3. So using the periodic table, we can actually figure out for the main group elements only, and when I say main group, I'm talking about these 2 columns and these guys here, the representative elements, so the S and the P's, not the transition. Okay? But the S and the P's, we can figure out what the valence electron should be based off where that element is on the periodic table. Okay? So let's apply it to what we see here. So bromine has 7 valence electrons. How do I know that? It's a halogen. All halogens will have 7 valence electrons. Okay? So what about the noble gases? Well, they have 8. How do I know they have 8? Well, I know they have 8 due to the octet rule. So what the octet rule is, everybody wants to be a noble gas. So all atoms want 8 electrons, because 8 electrons gives them a full outer valence shell. There's exceptions to this rule, like there is to every rule, and that exception, so except hydrogen and helium. So let's look at this a second. So why are hydrogen and helium an exception? Well, notice hydrogen and helium only have an s orbital. What's the max we can fit in an s orbital? 2. So hydrogen and helium only want 2 electrons, but everybody else has an s and a p. So everybody else of the main group elements want 8. They want to be just like the other noble gases, neon, argon, krypton, xenon. Okay? So to get to be them, they're going to have to form what we call ions. But before we get to that, let's look at the valence electrons. So I'm putting up here in green how many valence electrons each of these groups have. So the alkali metals, they all have 1 valence electron. Hydrogen, lithium, sodium. I know hydrogen's not a metal, but it still has one valence electron. That's why it's there. Group 2 here, the alkaline earth metals. Beryllium, magnesium on down have 2 valence electrons. Helium also has 2. That's why he's okay there right now. Going down to group 3, boron, aluminum on down. They all have 3. 4 valence electrons, 5, 6, 7, and then finally the noble gases at 8. So remembering these, as long as you skip the transition metals, should be pretty easy because you're just counting 1 through 8 of the representative elements. When we write electron configurations, part of what we're writing or part of what we're including are the valence electrons. Because electron configurations, these numbers here are representing the electrons. So how do we know which ones are the valence electrons? Well, in a picture of an atom, it's that outer shell, that outer ring. In the electron configuration, it's the highest level. Okay, so for bromine, for instance, what is the highest principal energy quantum number? 4. So I'm going to look at the 2 4s, not the 3D, the 2 4s, and it's these electrons here. So it has 2 valence electrons in the 4s and 5 valence electrons in the 4p. So if I add those together, 5 plus 2 gives me 7 valence electrons. Well, we just said bromine's right here. Bromine has 7, and it proves it with our electron configuration. So to figure out the valence electrons, you are just counting the highest energy level electrons. All right, so how does this help us? Well, I've said that valence electrons, they're the outer shell electrons, and they're involved in bonding, right? Well, oftentimes when we have bonding, we have a transfer of electrons. We said everybody wants to have 8, right? That's the octet rule. Everybody wants 8. Well, how do the other elements get 8 electrons? For instance, bromine, we were just talking about him. He only has 7. Well, how does he get 8? He's going to have to take one. He's going to have to gain an electron. When that happens, bromine's no longer going to be neutral. So now what we're looking at are ions. And ions are charged atoms. And they're charged because they are either taking electrons or losing electrons. So there's 2 different types of ions we're going to look at. There's a cation and an anion. And a cation is a positively charged ion, so positively charged, and it is positively charged because it is losing an electron. Now I know that that's counterintuitive. Usually when you lose something, it's a positive thing, or a negative thing, but what we're losing is a negative electron. So if you lose a negative charge, you yourself would be positive. Okay? So with an anion, you can guess what that's going to be. That's going to be the negative version. So now, negative is gaining something. So it's opposite of what you would think. But it's gaining a negative electron. So if you gain a negative, you're going to become negative. So this is gaining a negatively charged electron. So some ways to remember cation versus anion is for the cation, you can see A, and then this T, imagine it's a positive instead, a positive sign, plus sign. See a positive ion. So you'll know that cation is the positive one. So an example would be lithium with a +1 charge. That would be a cation because it's got a positive charge. For the anion, it's a negative ion. So a negative ion. So an example of this would be bromine with a negative charge. Well, we just looked at the periodic table and discovered that we could figure out how many valence electrons any of the main group elements had just by where they are on the periodic table. Well, we can also tell what charges they should have. By that I mean, should they be positive? Should they be negative? What magnitude? Is it going to be +1, +2? Is it going to be a -3 or a -4? Okay, we can use that to figure it out. And we use that in conjunction with the octet rule. So, for example, let's stick with bromine. Bromine is a halogen. So all halogens have 7 valence electrons, right? But how many do they want? 8. So if they have 7 and they want 8, what do they have to do to get 8 valence electrons? Well, they're going to have to gain 1 more electron, right? 7 plus 1 is equal to 8. So if they gain 1 more electron, if you gain an electron, you're going to become negative. So all the halogens are going to form a -1 anion. Because by gaining 1 electron to be a noble gas, they will then have a negative charge due to that electron they gained. So let's look at these guys, oxygen, sulfur, so on, that have 6 valence electrons. Well, they are 2 away from being a noble gas, right? 1, 2. So if they can gain 2 electrons, they'll be happy. They'll have a full octet. So they're going to be -2 charge when they form anions, because they gain 1, 2 to get to the noble gas. Now I bet you can guess with nitrogen and phosphorus what's going to happen with those guys, because they are 3 away. So they're going to gain 3 electrons, making them a -3 charge. We're going to ignore group 4 because they can be +4 or -4. So we'll only look at carbon, silicon in covalent bonds when we're sharing. We won't look at their ions. So that's why I'm ignoring that section. Now we're over here with the alkali metals, alkaline earth metals, and group 13A. So what do they do? Well, aluminum is going to form a +3. So notice now we went into the positive range. So why did I change? Okay, well we actually have some rules. Cations, the ones that lose electrons. Metals are the ones that tend to lose electrons. And now we're in metal territory. Remember, there's that zigzag line that separates the metals from the nonmetals. Nonmetals are over here. Metals are aluminum on over. And metals lose electrons. And if you lose an electron, you're going to be positively charged. So that's why aluminum's a +3. Okay? Well, the nonmetals then, we just saw, were the anions, right? They all formed negative charges. So the nonmetals being on the right side of the zigzag line all have negative charges because they're gaining electrons to be a noble gas. So that means aluminum is losing 3 electrons to become a noble gas. And notice, he has 3 valence electrons, so he's getting rid of all 3 of those to get in a noble gas state. So when we get to the alkaline earth metal, they have 2 valence electrons. So how many do you think they're going to lose to get to a noble gas state? They're going to lose 2 to become a +2 cation. Alkaline metals, +1. All right. So now we're going to practice a few questions using this information. So here's a question similar to what you would see on your homework. It's a multi-part question. And then once we cover this question, we'll look at one of the last topics, isoelectronic. So say you had a question where it asked for the total electrons and valence electrons better marker in what atom have we not looked at? Let's do oxygen in an oxygen atom. At what is the number, principal, energy, level. So, long question, sorry, but had a few people ask about this. So I wanted to address it, but we needed to know all that information first. So, we're going to do a whole bunch of things with oxygen. First, we're going to figure out the total electrons. We're going to figure out how many valence electrons it has. We're going to look at the number of principal energy level it's in. And we're going to look at what type of ion it would form. Okay, so a whole bunch of things. So let's look at oxygen. Notice it's neutral oxygen, so it doesn't have a charge on it yet. So how many total electrons? So when we're looking at total electrons, that's that entire electron configuration. Okay, so we actually don't need to write the electron configuration of oxygen to figure that out. This would be the electron configuration of it, but we don't need to look that up because if we know it's neutral, our protons are going to equal our electrons. So if we know the protons, which is the atomic number, we know how many total electrons oxygen has. So oxygen's atomic number is 8. Since it's neutral, that means it's going to have 8 electrons. So that's total. Different than valence. Because remember, valence electrons, we said, were just the electrons in the highest energy level, that outer shell. So since 2 is the highest energy level of oxygen, that means it's just these electrons here. So how many valence electrons does oxygen have? 2 plus 4, so valence electrons is equal to 6. And we can also figure that out because what we just counted here, these numbers in green, tell us how many valence electrons. And oxygen is right underneath the 6 here. Okay? So we have total, 8. We have valence, 6. Next, it asks, what is the number of principal energy level? So what's the highest energy level? What row? What period is it in? That's what it's asking. What period? Well, it's in period 2. Right? If we look at the periodic table, it's in period 2, so that's all it's asking for. So for the principal quantum number, represented by the letter N, we're going to put 2. And that's the level in which the valence electrons are found, right? Level 2. Those are the valence electrons all coming together. All right, now next, what type of ion would oxygen form? So remember, ion, we're asking charged component. Ion was charged. So what charge is oxygen going to form? Well, it wants a full octet, so it's going to gain 2 electrons, and it's going to form a -2 charge. But more than that, it says what type of ion. So I know it's oxygen with a -2, but what is this? It's a negative. Is it a cation, or is it an anion? So a negative ion is an anion. -2 to be more specific. All right. So now, taking this information, let's look at the definition of isoelectronic. So that's another question on your homework that I think is asked a few times. So, to do that, we need to look at the definition of isoelectronic. And I talk about this in the PowerPoints as well. So I know a lot of this is kind of review from the PowerPoints, but some people are visual, some are auditory learners, so I like to put both up. So isoelectronic. So these are atoms, and they can be charged atoms or neutral atoms, but it's just atoms that have the same number of electrons. And let me be more specific, same number of total. So we're not looking at just valence, total electrons. All right, so to figure this out, let me start by saying anions, which are negative ions, are isoelectronic noble gas in the same row. Okay, what do I mean by that? I said the anions, negative charge, so we're looking at the nonmetals, right? So the halogens here, they all form a -1 charge. So let's look at fluorine, let's isolate fluorine. So fluorine, since it's an anion, since it's going to form a -1 charge, it's isoelectronic, so it has the same number of electrons as the noble gas in the same row. So that means fluorine, when it has a -1 charge, has the same number of electrons as neon. Because that's the noble gas in the same row. Let's try another one. Let's do phosphorus. Okay, so phosphorus forming a -3 charge, so it's an anion. So phosphorus with a -3 is going to have the same number of total electrons as the noble gas in the same row. So argon in this case. Okay, so this is a rule for anions. Let's look at cations. Positive charge, right? So they're losing electrons. So we're looking at the metals. They are isoelectronic with the noble gas in the row above. Why the row above? Because they're losing, so they have to go up a level. Okay, so let's try one. Let's do beryllium, Be. So beryllium's a metal, it's going to lose electrons, it's going to become a cation. How many electrons is it going to lose? Well, it has 2 valence, so it's going to lose both of those. So it's going to form a +2. So my most probable ion for beryllium is going to be Be +2. It's going to lose those 2 valence electrons. Well, what noble gas is it isoelectronic with? We're not going to look at the noble gas in the same row, but the row above. So since beryllium's in row 2, it's in period 2, we're going to look at the noble gas in period 1. So what's the noble gas in period 1? Helium. Okay, let's try another one. Let's do sodium this time. So sodium, alkali metal, has 1 valence electron. It's going to lose that 1 valence electron to become Na+. So now it's a cation because it has a positive charge. It has lost an electron. It is a metal. What noble gas is it isoelectronic with? The row above. So sodium's in period 3. We're going to look at the noble gas in period 2. So it's isoelectronic with neon. All right, let's try some pairs. So far we've just been looking at ions and the noble gas that they're isoelectronic with. But it's not always going to be a noble gas that you're comparing it to. So I have a few pairs written down. I'm going to keep this up so we can use it if we need to. Let's see. PO2 minus, AT minus. So with all these pairs, we're going to look at them and we're going to say, are they isoelectronic, yes or no? All right, I'm just going to write all of them down. So I got that one. I'm going to do oxygen and the nitrogen ion. Helium and krypton, not potassium. And then last but not least, we'll do potassium and chlorine. All right, so we want to figure out if these atoms are isoelectronic. We can do this in a couple different ways. Okay, we can write their electron configurations. If they have a negative charge, we're going to be adding electrons, because the negative charge means they have extra. If they have positives, like this guy over here, we're going to be taking electrons out of their electron configuration. So that's one way to do it, right? We can also see what noble gas they're isoelectronic with, just like we did up here. And if they're the same noble gas, that means they are isoelectronic with each other. That means they have the same number of electrons. So let's look at PO2 minus. Not on here, but it is, looking at the periodic table over here. Where is he? It's number 84 in row 6. So right here, this is where PO is. So the reason he has a 2 minus, oops, I put him in the wrong spot. Good thing I said the reason he has a 2 minus. He's right here. So the reason he has a 2 minus is because has 6 valence electrons, and he needs 2 more to be a noble gas. Okay? So, what noble gas is polonium isoelectronic with? Well, it's going to be the gas in the same row since it's an anion. So, what is the noble gas in period 6? It is radon, Rn. Right, now let's look at At minus. And At is actually right next to polonium. So it's got 7 valence electrons. It needs 1 more. It's why it forms a -1 charge. But notice, since it's an anion and it's in period 6, it's going to have the same noble gas as polonium. So since they have the same noble gas, yes, they are isoelectronic. Let's look at this next example. We got oxygen, nitrogen. Both nonmetals, both form negative charges, so they're both anions. So when we compare these two, we know that they're going to be isoelectronic with the noble gas in the same row. So what row is oxygen in? It's in row 2. So neon's going to be its noble gas. Well, look at there. Nitrogen's also in row 2. So neon as well. They match. So yes, isoelectronic. This one is going to be a little easier because one of them is a noble gas itself. So all we have to do is check to see if this guy here, this anion, is isoelectronic, if that's its noble gas. So it's an anion, negatively charged. So we're looking at the noble gas in the same row. So where is Te? So when I look at my periodic table, Te is in row 5. It's in period 5. So looking at the noble gas in period 5, so it's this guy here, the noble gas in period 5 is xenon. Krypton's up here in period 4. So Te, its noble gas is xenon. Is that the same as krypton? No. So this would be, no, it's not isoelectronic. They don't have the same number of total electrons. All right, the last example, make sure I'm not running out of time here, is potassium with a +1, so we're seeing our first cation, and then chlorine with a -1. So let's look, what noble gas is potassium isoelectronic with? Since it's a cation, we are looking at the noble gas in the row above. So potassium is in row 4. It's right underneath sodium here. So we're looking at the noble gas in row 3, and that would be argon. What about chlorine? Chlorine is in row 3. It's an anion, so it's going to be isoelectronic with the noble gas in the same row. So chlorine's here, group 3. What's its noble gas? Argon. Do they match? Absolutely they do. So yes, they are isoelectronic with each other. And just to make a little more sense of this, we're going to draw the electron configurations of these guys to prove that they have the same number of total electrons. Okay, so potassium with a +1. So to write that electron configuration, we're going through 1s2, 2s2, 2p6, so on and so forth. So we're going to keep going. 2p6 brings us to neon. 3s2 brings us to magnesium. Then we hit the 3p's. We go all the way through them, so 3p6, we're at argon. Then we get to the 4s. And notice, if it was neutral, this would be that 1 valence electron that potassium has. But since it has a +1 charge, what it means is it lost that valence electron. So it doesn't have that guy. It's not neutral anymore. So we lose 1 electron. So this is the electron configuration of the potassium cation. So let's see if this matches up with chlorine when it has an extra electron. So let's look at chlorine. We're doing -1. We're not doing the neutral right now. So chlorine, same pathway. 1s2, 2s2, 2p6, 3s2, 3p, and it's usually 3p5, right? This is its neutral configuration. But we're not looking at the neutral, we're looking when it has a negative charge. And that negative charge says you have an extra electron, chlorine. So instead of 3p5, I'm going to add an extra electron, and it's going to be 3p6. Notice, exactly the same. Their electron configurations are the same. That means they're isoelectronic. If I added these numbers, they would equal the same. So what number are we looking at? 18. So it should equal 18 down here, and it should equal 18 up here. This is total electrons. So, last thing I want to cover are periodic trends. And I'm only going to focus on one of them. There are 4 different ones in the PowerPoints. By all means, look at them. But the one I want you to focus on is atomic size. Clear some room on my periodic table to show that. And we've actually talked about this a little bit already when we talked about the principal quantum numbers. So atomic size, it is going to decrease from left to right on the periodic table, meaning atoms get smaller. Let's use a weird color. So I should write it the other way, huh? So it's increasing this way. Increase size. And it's going to increase as you go down. So notice increasing as you go this way, increasing as you go down. So what is the largest atom on the periodic table? It's not francium because he's radioactive, but if he wasn't radioactive, it would be him. So it's actually cesium here. So let me erase this success. So cesium is the largest. And then fluorine, because we're not going to look at the noble gases, fluorine in this upper corner is going to be the smallest. So let's look at some of the reasons for this. Well, cesium being the largest, or increasing as you go down, makes sense when you know the shape of an atom. We have a nucleus. We have rings around that nucleus that hold the electrons, those principal energy quantum numbers on the side here. Notice as you go down, you're adding principal quantum levels, which means you're adding rings around the atom. So the more rings you add, the larger your atom's going to be. So it makes sense that it's increasing as we go down. Okay, well, why is it decreasing as we go from left to right? Okay, well, the reason for this is due to electronegativity, and that's one of the trends that you see on the PowerPoints as well, and we're going to cover this in great detail in Chapter 3. But as you go to the right, the electronegativity is increasing. Why? Because these atoms want electrons more. That's what electronegativity is. It's the pull, the need, the want of electrons. So these guys all want electrons because they're trying to be a noble gas, right? That's why they have negative charges when they form ions. So fluorine is going to be the most electronegative atom on the table because all it needs is just one electron. It's almost there, so he wants it the most because he's closest to being there. Okay? So that's why fluorine is going to be the smallest. Since he's so electronegative as well, he only has 2 rings around him, so he's smaller that way. But since he wants the electrons so much, his nucleus is holding those electrons really tight. He doesn't want to give any of them up. So since he's holding those electrons tight, those shells are being almost shrunken, held tighter to the core, to the center. So that's why he's going to be the smallest. So how are we using this? If you're given a list of elements, you need to put them in order of atomic size. So for instance, let's do these guys. If I say, okay, those atoms, put them in order of increasing. So let's put them in increasing. So that means I want smallest to largest, okay? So what's my smallest out of that group? Well, you would have to look at your periodic table. And we're looking at period 4, and this is gallium, germanium, arsenic, selenium. Might as well throw bromine in there too, why not? So we said that size decreases as you go this way. So what it means is it's increasing as you go that way. So what's the smallest in this period? It's going to be bromine, because as we go to the left, it's going to increase. So bromine's going to be our first, and apparently I already put him in there, didn't realize that. So he's going to be the smallest. Next we have selenium. Next we have arsenic. And then next would be GE. So this would be the correct order, with the largest, greatest being germanium. So that's how we're using the trends. So that covers all the material in this section. If you have any questions, post them on the discussion board, but if no one's answering them, by all means, send them to me. I do check the discussions, but I don't check them daily. And I like try to wait to see if one of the other students in the class are going to answer them before I butt in and start answering. So let me know if you have any questions. And don't forget to do the homework questions and the discussion before Sunday at midnight.